share the screen. Let me see if I can find it. Yeah, it's here. That's it. Okay. Okay, so yield line analysis of slabs. Everything that we did so far was to do with frames and beams made of steel or metal. Yeah, so that was the plastic theory of structures. And if you remember, they were one of the assumptions. There are a number of assumptions for the plastic theory of structures. One of them, do you remember what was one of them to do with the materials? What's the assumption we used for plastic theory of structures? Very important one. The material is homogeneous and isotropic. Do you remember? Yeah? The material is isotropic and homogeneous, which is the case of steel and more, most metals like aluminium and so on. Yeah. So that's a key assumption. That means that you cannot use the plastic theory of structures for frames made, for example, of concrete. Yeah. You can only use it for steel structures, right? Now, for reinforced concrete structures such as slabs, we use a different method called the yield line. What you will see that there are a lot of similarities between the yield line analysis and the plastic theory. And as we go through the theory and explaining it, you will see there are some really similarities, because both methods use the ultimate state. Yeah, they are not elastic. They are really plastic. You see what I mean? They use the ultimate state. Okay. So the plastic theory uses a bilinear distribution where we use the we design using MP, the plastic moment MP. Okay. Similarly here, with the yield line analysis of slabs, we are going to talk about the moment of resistance. Okay. So let's go through some of the basic principles first. As you walk on the pavement, you've seen this before, yes? Right? Slabs cracked. And you see all kinds of patterns. Why do we have different patterns? Why do we have different crack patterns? Why?
Different points of impact.
Yeah, okay, bit more. Why we don't get the same pattern everywhere when they crack?
The material's not identical throughout.
Assume it's identical. Yes, it's one of them actually, but it's not key. Yes, that's a good one. So because the mix may not be exactly the same. Correct? Yeah. What else? Do you think all the slabs are supported exactly the same way? Yeah, they are resting on soil, isn't it? But they're not supported exactly in the same way. Yeah, because maybe some parts you got more soil than other, and so you don't have a uniform. You haven't got a uniform support which is identical for all the slabs. So obviously there is the mixing of the the slab manufacture of the slab itself. Okay, and the mixing is not exactly the same. The other one is they're not supported in exactly the same way, and also they're not subjected to exactly the same load. Okay, so you have got there a number of parameters which makes the yield lines. We call these yield lines. These cracks, we call them yield lines. So that makes the yield line patterns different from slab to slab. The key one are the support conditions. How the slab is supported. Okay, is it supported on 4 edges? Is it supported on 2 only? Is it supported on 3? Is it fixed on 1 and simply supported on others? And all these differences will make a difference to the kind of pattern that you get. Okay. Now, so we use the plastic analysis. I should call it yield line analysis. Sorry, I removed that plastic. Just call it yield line. Sorry, it's a mistake. So we use the yield line analysis for concrete slabs, especially. It's very, very powerful method for two-way spanning slabs. We use it for, we'll do an example of one-way spanning slab, but we certainly, it's certainly more useful when you have two-way spanning slabs. And the limit state principles are based on the ultimate collapse load. So we are analyzing at ultimate state. And the method, the yield line analysis, establishes a relationship between the ultimate moment, or the moment of resistance, and the applied load. So it gives you a relationship between the applied loading and the moment of resistance of the slab at collapse. Are you familiar with EC2?
Yeah.
You have used it for reinforced concrete, isn't it?
Yeah.
Yeah. What does EC2 give you for reinforced concrete beam? What does it give you? You have a beam, okay, and you know the reinforcement, you know how it's supported, everything. What does EC2 give you? What does the code give you? What does the code give you? Moment. Do you agree? It gives you the moment. Do you remember that equation n equals 0.15 whatever or not? No? 2 years ago. Anyway, Eurocode or any code, okay, any design code will give you the moment of resistance. It doesn't give you the load. Okay? So when you use the code, it doesn't give you the load, it gives you the moment of resistance. Okay? Is that clear? And there is an equation in Eurocode. If you go to a Eurocode and you look for a slab or a beam, a reinforced concrete beam, you find an equation for the moment of resistance. Okay? But it doesn't give you the collapse load. The yield line analysis, the yield line theory, gives you that relationship between moment and load. So with the knowledge of the moment from the code, you can then determine the collapse load. Is that clear? Yeah. So that's what the yield line is about. It gives you that relationship, and then so when you combine it with the design code, whether it's Eurocode or any other code, then you can get the collapse load from that. Okay. So and inversely, if you happen to know the moment, you can always if you happen to know the load, you can always determine the moment of resistance. How could you determine the collapse load? If you don't know the moment, how would you determine the collapse load? You've been doing it with David for the last, God knows. What did you do in the lab? Testing, isn't it? So if I take a slab, if I test it, I can determine the collapse load, isn't it? Yes, I can determine the collapse load. This load here, I can determine it from testing. And if I can determine the load from testing, then with the yield line, which gives me the relationship between collapse and moment of resistance, I can determine the moment of resistance. Can you see the three different methods? You've got testing, you've got the code, and you've got the theory, right? If you use the code, it gives you the moment. You can determine the collapse load, okay? Or if you do a testing in the lab, it gives you the collapse load, and therefore you can determine the moment. All right? I'm just saying this so that you understand how the practicalities of the theory. It has got practical implications. You can use it in practice if you are designing a slab for a floor in a building. Okay, you can actually use this method to help you with the design. Some principles, yield lines. How do yield lines develop, and how does the slab collapse? Under-reinforced sections have the capacity to develop significant curvature at collapse. Okay. In other words, simply put, if you've got a slab, reinforced concrete slab, you've got the reinforcement in the slab. Okay. When does the yield lines start to appear? When? So if I have a slab and I start loading it, when will the cracks, if you want, or the yield lines start to appear? Yielding. When the reinforcement, when the steel bars start to yield. Okay? When the steel bars, the reinforcement reach the yield point, and the steel has started to yield, this is where the cracks, this is where the yield lines will start to appear. Okay? So this is why I explained. The second point is that the cracks are the yield lines. Okay, so we refer to the cracks as yield line, and when we have sufficient yield lines developing, obviously this is when the slab collapses as a mechanism. What's the analogy in the plastic theory of structures for cracks? Yield lines. What is the analogy in the plastic theory? Plastic hinge, exactly. If you remember, we used to say when you have sufficient plastic hinges forming, the frame or the beam will collapse, isn't it? Completely. It's exactly the same here. We talk about when you have sufficient number of yield lines forming, then you have collapse. So this is the first analogy that you can see with the plastic theory of structures. Analyzing the yield line mechanism. In the plastic theory, analyzing the collapse mechanism allows the determination of the load, of the moment-load relationship. In design, how do we design a slab? First of all, we need to postulate a yield line mechanism. In other words, we need to make a good guess or decide on a yield line mechanism. The second step will be then to determine the relationship between the moment and the ultimate load. And finally, you can design the slab as I have explained earlier. Okay. One way. Let's start with the most simple example, which is a one-way spanning slab. So what we have here, we have a slab, a rectangular slab, and the slab is simply supported on two edges, on two sides. Okay. And it's free on the other parallel sides here. And this it has got reinforcement as shown. If you take a strip here, a tiny, a thin strip of the slab, this is what you see in cross section. You agree? So it's like a simply supported beam. So what's going to happen? Imagine you've got a uniformly distributed load applied onto the slab. Do you agree that it will fail in the middle here? Yeah. So what happens is you will have a formation of a single yield line in the middle. Why in the middle?
Because the supports are at the ends.
I mentioned the word earlier. I don't know how you paid attention to it. Curvature, maximum curvature. Yeah. So when your beam curves, the maximum curvature is in the middle. It just happened that it's the maximum bending moment and the maximum deflection are in the middle. But it's not always the case. You don't always get the maximum moment and the maximum curvature and the maximum deflection at the same point. And take the example of a propped cantilever, isn't it? The maximum moment is at the support, but the maximum deflection is at the free end. Right? So from now on, please think of in terms of curvature. Is that clear? So here, the maximum curvature is in the middle, and this is where the crack or the yield lines appears. Okay? So this is a very clear, simple example of a one-way slab. Okay? Let's see. This is a two-way spanning slab. This is a rectangular slab, the same slab, simply supported on four edges, on all four edges, okay, on all four sides. And this is, if you take this slab to the lab and you simply support it on four edges and you load it with a UDL at the top, this is the mechanism that you get. Provided your slab is perfect, in other words, you have a homogeneous mix of the concrete and the reinforcement is the same and everything is perfect, that is This is the yield line pattern that you get for a simply supported slab, rectangular slab on 4 edges. Okay, and this is a two-way spanning slab because it spans in this direction and in this direction, and that's the correct, that's the yield line pattern. Okay, how do we know how a pattern forms? Okay, I think there are some rules that we can follow. Number one, yield lines end at slab boundaries. Look here. Can you see the yield line here where it stops? It stops at the boundaries. See that? Yeah. So these are the slab boundaries here, there, and there, and this is where these yield lines stop at the yield line at the boundaries. That's number one. Number two, yield lines usually assume straight. In reality, we know in practice, we know that the yield lines, the cracks, are not straight lines. Do you agree? They're a little bit, you know, like a zigzag. Yeah. But for simplicity in the theory, we assume that they are straight lines. Okay. So that's number two. Yield lines passes through the intersection of slab boundaries. It's very similar to the first one, basically, in this context. Okay. And the third one, the axis of rotation passes along lines of support and over columns. I'll come back to the columns in a minute. So the axis of rotation passes along lines of support, support. Let's look at this example here. Yeah, pay attention, please. This slab is divided into 4 regions by the yield lines. Do you agree? We have this region here, which is identical to this region, and we have this region on the left, identical to this region. Do you agree that the top region, this region here, rotates about this axis? Do you agree? Yes? Agreed? When it fades? Yeah? Because you remember the deflection is out of plane here. So this region rotates about this axis. For this region here, this triangle, the rotation, the axis of rotation is this one. Clear? Etc. Okay? So, and this is why it says here, the axis of rotation passes along lines of support. Okay? The symmetry in geometry and loading is also reflected in the yield line symmetry. In other words, if you've got the slab, if the slab is symmetrical, if the loading is also symmetrical, which is the case here, you have a UDL, so you have a symmetrical loading, and you have got a symmetrical geometry of the slab, then obviously you can see that the yield line is symmetrical about this axis here, the vertical, and this axis. Is that clear? So symmetry of loading and geometry of the slab will be reflected in the geometry of the yield line pattern itself. Okay? If there is anything not clear, please stop me, okay? Finally, yield lines start in regions of highest curvature. So the yield lines will start in regions or points of highest curvature. You see here. Where is the highest curvature for this slab? Where is the highest curvature? Center, you agree? Can you see this yield line here where it starts? It starts in the center, isn't it? Can you see that? So it starts in the center and then propagate, and it ends at the intersection of the support, as indicated here. See here, lines and at slab boundaries. So the yield line starts at the point of maximum curvature and ends at the slab boundaries, exactly as we have here. Okay, sorry. It starts at the point of maximum curvature and ends at the slab boundaries. Okay. In most of the cases, you don't even need to remember the rules because it would be so obvious. Because in our case, we'll be dealing with rectangular slabs or square slabs, so it's always you get a similar pattern like this, okay? Okay, we make a number of assumptions, just like we did with the plastic theory of structures. If you remember, we had a number of assumptions. Assumption number one, at the collapse stage, the yield, the steel reinforcement will be fully yielded along the yield lines. It's very similar to the plastic theory. Do you remember what we said? We use sigma y, isn't it? When we work out MP, right? So it's similar. Secondly, during collapse, the slab is deformed plastically and gets separated into regions. As we have seen with the rectangular slab, the yield lines split it or divide it into 4 regions. Number 3, the individual regions behave elastically and remain plane. In other words, what we assume that each of these regions, okay, when they deform, they don't actually collapse themselves or they don't deform, they just remain plane. Is that clear? They remain plane, okay? Number 4, there is a uniform distribution of moments along yield line. What does it mean? It means that along this yield line, the moment of resistance is the same. Along this yield line, the moment of resistance is the same, etc. Okay? So you have moments along the yield line, okay, is uniform. Okay? I mean, again, it's very similar to when you have when you have a frame, if you have a column, we say MP is the same, isn't it, for that column or that beam. So it's a similar thing here. The yield lines are lines of intersection of 2 planes, hence they will remain straight. It's obviously, all it means here is that the yield lines remain straight, okay? Deformations are very small. This is similar to the plastic theory. Do you remember plastic theory of structures? Deformations are very small. And the last point, again, is exactly the same as the plastic theory of structures. Shear and axial effects, the axial effects are ignored. In other words, negligible. So ignore the shear and axial effects. Any questions up to this point?
Leave it up there for a second.
Yeah. It's on Aula anyway, don't worry. So the shear and axial effects are ignored. I mean, there would be some effect, but what we say that the effects, but the slab behavior is governed by the bending moment, okay? And we ignore the contributions from the slab, from the shear and axial forces. I just want to cover some examples, okay? This here, top left, we have a slab which is simply supported on 4 edges and it's square. So if the slab is square, you get this yield line pattern, okay? We assume the yield lines are straight, okay? This is a one-way spanning slab, so it's supported, simply supported on these 2 edges. So obviously, what you have here, you have a yield line which is along the maximum curvature. So you have one single line of failure. This example, bottom left corner, we have a rectangular slab, but fixed on 4 edges. So fixed on 4 edges. So you have got the yield lines here in black pen. So what is in red here? What is in red?
Yeah.
What's in red? If it's fixed, what have you got at the edges? If the slab is fixed at the edge, what have you got at the edges? If you have a propped cantilever, what have you got at the support? You have a moment. So if the slab is fixed at the edge, what have you got there? A moment. Positive moment or negative moment? Is it a hugging moment or is it a sagging moment? Hugging moment. So, what's the sign? Negative. So the moment in the middle here, yeah, there, you have a positive moment. Imagine, think in your head of simply support. A beam which is fixed at two supports. In the middle, you have got a sagging moment, isn't it? Yeah. Positive, and at the edges, you have got negative moments, hugging. That's exactly the same here. It's exactly the same. So for your slab here, you've got moments in the middle, where you have the maximum curvature here. You've got a positive moment, sagging, and at the edges, because the slab is fixed at the edges here, therefore there are what we call negative yield lines. So these yield lines here, dotted lines, refer to the negative yield lines to distinguish them from the positive yield lines. So the negative yield lines here corresponds to the hugging moment. Is that clear? Yep. This one here, this example here is the same as this one, except that the edges the sides here are fixed. When these sides are fixed, in addition to the positive yield line in the middle here, you also have got negative yield lines corresponding to the hugging moment again. Is that clear? Yep. So this is a trapezoidal shape, no different of a rectangular shape. You can see that the yield line pattern is exactly the same, okay? It starts at the positions of maximum curvature and then spreads to the intersection of the supports. And this one is interesting here, this top right. What you have, you've got a slab which is supported on three edges and free on one edge. You have two possibilities. You have got either the yield line pattern in dark color, or you've got the yield line pattern in red. It all depends on the relative ratio of this length to this length here. Okay, depending on the relative ratio of this length to this length, you can get the one in dark color or the one in red. Okay, this is here slab that has got 5 edges. 4 are simply supported, and this edge is free. So how do you decide on the yield line pattern? Remember the rules. Rule number 1, the yield line starts at the point of maximum curvature. So I have somewhere here, I have a point of I have a starting point. So my starting point here is where the curvature is maximum. Then the yield line will spread to the points where of intersection of the supports. So it goes there, then it goes there, then it goes there. Okay, it cannot go this to this corner or this one, because this end is free. However, what you do, you extend this side and you extend this side, which is simply supported. It gives you a point of intersection, and then you join from the center there, from the point of maximum curvature to the point of intersection, and that gives you the yield line as shown here. Is that clear? Okay, so it gives us this yield line pattern. Finally, we talked earlier about the columns, and what we said that the yield lines go over the columns. The yield lines will pass over the columns. So what you have here, we have a slab. This is the slab, which is simply supported on these two supports, and is free on this support here. But it is supported on these two columns at the corners. So in that case, the yield line will start at the maximum curvature there. It goes to the point of intersection of the supports, which we have here. And then you extend the axis. This is the axis of rotation for this part. So you have an axis of rotation here, which I extended. Then we have an axis of rotation which goes over the columns, which gives me this point of intersection, and the same on this side. And then what you do, you join from the points of maximum curvature to the points of intersection. And this is the yield line pattern for this particular slab. Okay, so it's very easy. You just need to follow the rules. And there are two key rules that you need to remember. Number one, the yield line starts at the points of maximum curvature. Okay, here. And the yield line will then extend to the point of intersection of the axis of rotation, like we have here. Any questions? Is that okay? Anything at all? Okay, so this is where we get to the not tricky, but this is where you need to pay some attention, please. Slabs are not like beams. Slabs are 2D, isn't it? You've got two dimensions. It's not like slab, because with the beams, usually we treat the beam as unidimensional, isn't it? Yeah, along the length. Whereas slabs, really, you have got two dimensions, if you want, in the X and Y directions. And because of that, we have moments and rotations in two directions, right? So working in two directions can be complicated. To make it easy, we define the moments and the rotations in terms of vectors. So we are going to convert the moments to vectors, and we are going to convert the rotations to vectors. And then I can express a moment along a yield line as a vector, and I can convert a rotation about an axis again as a vector. How do we do that? For the moment vectors, we use the right-hand screw rule. So you do it with your right hand, and I'm going to explain how. For the rotation vectors, we use the left-hand screw rule. How does it work? Let's take a a one-way slab, and I'm going to explain for this slab. So this is your slab, okay? Simply supported on two edges, right? And it's going to fail in the middle here. So when the slab fails like this, what happened to this side here? This is what you see in a cross section. This is how the slab fails, right? Do you remember when we did the plastic moment, theory? Do you remember the direction of the moments there? Do you agree that these are the correct directions of the moments? Do you agree? Yeah, because remember what these are. These are moments of rotation. Moments of resistance. These are moments of resistance. What does it mean, a moment of resistance? A moment of resistance means if your slab is going to rotate in this direction, the moment will try and prevent it. So the moment goes against the rotation. So if the slab rotates in an anti-clockwise way, if the rotation is anti-clockwise, the moment of resistance is clockwise. See here? So this side, this part of the slab rotates clockwise or anti-clockwise? How is it rotating about this edge? Anti. So the moment is clockwise because it's a moment of resistance. Similarly, for this side of the slab, the rotation is clockwise, so the moment is anti-clockwise. Clear? Okay. So now, because we have a 2D slab, this moment here, can you see there? Along the entire yield line. So we have a clockwise moment here, this one here, okay? And on for this side, we have this anti-clockwise moment there. Clear? Now, concentrate on this side here, the right one. Concentrate on the right one. Okay, so this is the right side. Okay, and it's, you have a moment of resistance going this way, clockwise, right? So with your right hand, you do a clockwise. You do a clockwise direction with the palm of your hand, and the thumb will give you the vector. See that? And that's the direction for the moment vector. So you use your right hand. You make the direction of the moment, in this case clockwise, and your thumb will give you the moment vector. Is that clear? Yeah. If you do that for the, if you do this for the left side, for this region here, always using the right hand, you can see here we've got a moment this way, okay, and the thumb pointing towards me here gives the moment vector. Okay, the key thing to remember is that you use the same hand, right hand, for both regions, for all regions. Okay, you always use the right hand for all regions of the slab. So you mimic the direction of the moment with the palm of your hand, and the thumb will give you the direction of the moment. Is that clear? Yeah. What you notice this. Can you see these two vectors? They are equal and opposite because we have equilibrium. Okay. Just in the same way, the moments here are equal and opposite for equilibrium. You can see that the direction of the vectors are also in opposite directions, so they are in equilibrium. Is the moment vector clear? Clear? Now, let's go back to this region here, this part of the slab. Do you agree that it rotates about this side, about this edge? Do you agree? Yeah? Do you agree? Yeah. So this is your slab. So I'm looking at this part here. Sorry. Oh, that's scary, isn't it? So we look at this part here. We go slowly. You go slowly. Yeah, you digest it very, very slowly. You will be all right. So this is the slab. This is the left part. The right side of the slab here, right? It's rotating about this side, and it's rotating in this way. Okay, this is the axis of rotation, and it's rotating in this way. So the rotation is anti or clockwise? This here. Is it a clockwise rotation, this slab? Does it rotate in a clockwise or anti-clockwise way?
Anti.
You agree it's anti-clockwise?
Yeah.
Yeah. Look here. Use left hand. So now clockwise. So I do anti-clockwise. See that? Anti-clockwise, and the thumb will give me the direction of the rotation vector. Clear? Yeah. After you've done it for a few examples, believe me, you don't need to do it by hand because it happens here. Yeah, I'm just showing you how it does work. But I tell you from my experience, once you've done a few examples, it would be you just think about it. You say, okay, it's clockwise, so it's going this way. Yeah, but for now, you can use your hand if you want. So on this part here, we've got an anti-clockwise rotation. So using the left hand, you make an anti-clockwise rotation with the palm of your hand, and the thumb gives you, as you can see here, the direction of the vector. And you use the same hand, the left hand, for the left part here. Again, you can see it's rotating in this direction like this, and the thumb pointing towards me there. Again, what do you notice? You notice that they are opposite direction. The vector rotations here are opposite direction, but they are in the same direction with the moment within the same region. It's important to make these observations because in the future you don't want to do it for every single region. Once you've done it for one region, you can deduce the rest, okay? So it's worth making these observations. You can see here we've got the same vector, the same direction for the moment and the rotation vectors within the same region. Are the conventions for the vectors clear, please? Any questions? Okay, now, so what I've done here, that's the same example. This is a a single span slab, one-way span slab. So it's simply supported on two edges, on two sides, and free on this side here. Okay. Now, these are the vectors that we have just obtained from here. Okay, these are the vectors for the moments, and these are the vectors for the rotations, which I have got here. Okay, shown. This is not moment in brown here. This is just showing the rotation. Okay, so these are the moments. We have M and N. What you need to remember, please, very, very important, the units. The units for moment in the yield line analysis, the units for the moment, what are the units for moments in general? Kilonewton meter, you agree? However, because the moment is along the yield line, so the units are kilonewton meter per unit length. In other words, kilonewton meter per meter. Clear? And the UDL, there is a uniformly distributed load applied onto the slab. What is the unit of UDL in general? Kilonewton per meter. But in this case, for a slab, the UDL will be kilonewton per meter square, because the UDL is applied onto the entire slab. Okay, so it's per unit area, right? Okay. So internal work. Now here you will see the similarity between the plastic theory and the yield line. It's very striking how similar they are. In the plastic theory of structures, what did we used to do for the internal work? What did we do? Remember? What do we do for the internal work in plastic theory? MP times theta, isn't it? We take the moment times it by the corresponding rotation of the hinge. Yeah, we are doing exactly the same here. So here we have this yield line. For this region we have, this is my MP, okay, between brackets. So this is M, that's the moment. Why do we multiply it by alpha L? Alpha L is the length of the yield line, okay? Because remember, M is kilonewton meter per meter, so you need to multiply it by the length. Okay, we have L in this direction, and we have alpha L in this direction. Alpha is just a coefficient. It could be 0.5, 0.4, whatever. Okay, so you multiply M by alpha L by the length of the yield line on which the moment is applied. So this is effectively your MP in the plastic theory times theta. Okay, which is the angle here. Okay, we assume because we have symmetry, so the angle there and there will be the same. Okay, there is a yield line in the middle, so we have theta and theta, M and M, so you have M theta plus M theta, except that you need to multiply by the length because of the units of the moment. Is that clear? Otherwise, you can see that it's really the same as the plastic theory. Okay, it's just because of the units, you need to multiply moments by length and UDL by area. Otherwise, it's the same. And you can see it here actually. This is exactly what we did for the external work. We take the UDL and we multiply it by the area. And the area of the slab is alpha L times L. So you have alpha L times L, that's the area of the slab on which the UDL is applied. So you have UDL times area times, do you remember when we have UDL? What did we say? We take the, what displacement? What displacement do you take if you have UDL? In the plastic theory, what do you do? If you have UDL, what displacement you take? The average. Do you remember? You take half the displacement. Yeah? If you have a concentrated load, it's the load times the corresponding displacement. But if you have a UDL, it's the UDL times the average. You take the average displacement. And this is exactly what we did here. It's that displacement here halved. And that's it. That's the extent of work. So if you want, it's the UDL times the average displacement, except that you multiply by the area of the slab because of the units again. When you simplify here, you get WL squared, and then you have delta, and then you have alpha, and then you substitute. Can you see a delta? Is L over 2 theta, same as before. So you have delta here, the displacement is L over 2 times theta, which I have substituted here, okay? And when you simplify, it gives me W alpha L cubed over 4 times theta. For equilibrium, you equate the external work with the internal work, which gives M WS squared over 8 when you simplify the alpha and you simplify L from this side. Okay, the theta obviously will cancel, so you have MWF squared over 8. Does this answer surprise you? If you have a UDL on a simply supported beam, what's the maximum bending moment? If you have a beam of length L with the UDL, what's the maximum bending moment? Do you remember it? Do you remember WS squared over 8? It's the same. So if you have a beam, if this was a beam with the UDL W and length L, the maximum moment in the middle will be WS squared over 8. It's exactly the same. The only difference here is that your moment is kilonewton meter per meter, and your UDL is kilonewton per meter per meter. Otherwise, you get exactly the same expression if you take a strip of your slab as a beam. So what we have seen here, we have seen the analogy between the yield line analysis and the plastic analysis, and also you can see that you're getting the same results we used to get with the plastic theory if you were analyzing a beam. Any questions? Okay. Do you want a break? Because we are going to do a 2D slab now, two-way spanning. Do you want a break? Okay. Any questions? Any questions on this first one? No? Okay. Actually, I want to give you a 3 minutes break or 5 minutes. You know why? Because I'm being selfish. So I'm going to ask you to do the survey.
No break. No break.
It's very important. I got only about 26% of people who have actually done it. It's not good.
I didn't mind.
Would you mind going to log into your mobile phone and do it? It doesn't take half a minute to do, please.
No break, no break.
Sorry?
No break.
You've done it. You can have a break. Enjoy your break. Okay? Those who haven't done it are punished. You do it. Can you do, please, the survey, please? Please. Thank you. We just pause about 5 minutes. Yeah? 5-7 minutes to complete the survey. Please do it. Please. Thank you. You just find the link. If you click on the link on that email you receive, it should take you straight to the survey. And honestly, it doesn't take 30 seconds to do it. Okay? If you want to write comments, you can do that. Please, can you do it, please? He's doing it. Are you doing it? Are you doing it? You do it. Come on. Get your phone. How many people have done the survey? You can have a break.
Take it.
Well, I told him to be
Thank you.
probably even
I'm going to upload this Friday. I'm going to create a folder called extra tutorials. So there will be questions with answers, solutions to prepare you for, so you can practice it for the exam. Okay, I do this Friday.
yeah. Oh, Harry and you, yeah, Harry and you are ready.
How much is that? I'm gonna have a
Nina's didn't do it. Nina didn't do it yet. What? The Lucy fan. Nina's like, no.
No Facebook survey.
No meta, not Facebook. It's no meta. Yeah. Nina's a teacher. Very good. I think I missed it.
So that would be 2 weeks. So we'll find
Not that much. Oh yeah, so it's Tuesday.
So which one is first? This one. This one is first. Second.
Projects.
Yeah, there's that.
Yes, sense is good to go.
Yeah, I mean the contract one should be bad.
No,
It's
that's
just this
common.
one. Yeah, they're all open. Yeah, but these like you have to know what you're doing. But,
You just need to know. Yeah.
And then if the transport comes out weekend and we just allow you to write it,
Put some comments. I like reading comments.
my area and then I'm going to walk into this.
I know the days were quite long.
Yeah, but you don't like it once. Also the house, yeah. Well, today's interesting. I was 2021. Like, I remember I was thinking in my head with this.
Yeah, it's the common ones. And I had to get a ticket. Have it go. I'm like 2 minutes away from the station. Cab was £41. Cab was like £10 a day. So it was actually like £6 a day. And I was like, never again. The actual total I paid, they paid £62.75. No, I never had one. I've been driving since first year, so I never needed to drive one.
You don't work. You don't train like that. honestly, just not work. When I went in person, it works, but on that app, it works.
Just get back.
Yeah, it's too long, just wait on that. I know you just hold off.
Yeah. I don't know when it was. We missed the version before the advanced trains.
Yeah.
Something crazy. Could be something that was 2% so done. Yeah. People used to be so excited. Yeah. I know what it is. I still was £2 milk card. I get that. We're gonna write your comments. I write comments. I like when the suits is here. I do not like 4 hour lectures. I do not like teach me the lecture.
Is everyone back? Let me start.
I said like
I think there are a couple of people here.
let's start.
Okay.
He want us.
Oh, Yasmin's not going to let that go.
I think we're gonna spend
Yeah.
we like
When you got to see the rag with it involved.
yeah.
I think we should do it twice tomorrow on the
Sorry, I'm unemployed. Harry. No, I finished at 11. I'm in by 11:30. I think we look at the whole day. No, don't take your time. Sorry, no reason. Late selections. I don't want to finish this game anymore. I want to finish at 4. I hate the finish. Yeah, I get hungry and I'm talking about food. My life. What I'm doing when I get home. That's always me.
On the recording.
As long as we have everything in this project.
Okay, thank you very much. All right, let's finish this. Okay, we've got about 40 minutes, and I think we should finish it by then. So, two spanning. So two-way spanning slab. I'm going to go through it very, very slowly again. So if you have any question, just stop me. Right? So now we have a rectangular slab simply supported on all 4 edges. Okay? And as we said earlier, this is the line pattern, starting where the maximum curvature is and then spreading towards the intersection of the axis of rotation here and the supports. Okay? So it divides the slab into 4 regions, which I have called A, B, C, D. A and C, in terms of geometry, are identical, and similarly, D and B are identical in terms of geometry because we have symmetry in both directions. For this particular examples, given are the moment in the x. So this is the x-axis. I call the x-axis this axis here. So the moment of resistance in that direction is m, is given, and the moment of resistance in the y directions, this is this direction here, is given 0.4 m. Right? So these are given. Right? Okay, then the slab dimensions, we have 3 meters in the y direction, and we have 4 meters in the x direction. The yield line here, starts at 1 meter from this side, and similarly on the left, the yield line starts at 1 meter from from this side here. Again, that's given. I'm going to show you next week, okay, how to find the optimum this optimum distance. But for this example, the dimensions are given to us, and the yield line pattern is given to us. Okay. Now, the first thing we are going to do before we do the internal and external work for this slab is we are going to determine the moment vectors and the rotation vectors for each region. All right. I'm going to show you now that how, if you do it for one region, you can actually deduce it for the other regions, because there is some logic into the system. So let's start with region A. Please pay attention. Just focus on region A only. Okay, for now. This is region A here. Okay. The axis of rotation is this. This is, so A rotates about this axis. So I'll do them. Let's start with the easy bit, which is the vector here, the vector rotation. Do you agree that the A, this is region A, okay? This is region A. This is the edge. This is the axis of rotation. So A will rotate like this. Do you agree? Yes, it rotates like this. Now I use the left hand, and this is the rotation of A this way. Look. So the thumb gives me the direction of the vector. Is that clear? So use the left hand, that's the rotation with your palm, right? And the thumb gives you the direction of the vector. Is that clear? If it's not clear, please say so. Is that clear? No? Use your hands. Get a piece of paper. No? Look, this is region A. This is region A. Okay? That's A. It's rotating like this. Do you agree? When it deforms, it rotates like this. Yeah? So it rotates like this. This is the left hand. So this is the rotation of region A. Is like this. Okay? That's the thumb for the direction of the vector. Clear now or not? You need a bit of practice. Yeah? So you just look at how it's rotating. The direction of the rotation will be the palm of your hand, and the thumb gives you the direction of the vector. So look. Clear? Yes? Now, look. Now let's look at now. Let's look at now the yield lines. We have this yield line, this one here, and this one here for region A. Okay. What is the direction of the moment along this yield line? What is the direction of the moment of resistance for region A? Is it going into the screen, or is it coming out of the screen?
Into the screen.
Is it coming this way into the screen, or going into the screen, or is it going out? Look, this is A. It's easy. Look, this is region A. This is how it deforms. You agree? So the moment is. Do you agree that the moment is like this? The moment of resistance. So with the right hand, this is the moment of resistance, and the thumb is in this direction. Clear? Yeah? And the same applies to this side here, where you have the moment is actually this way. That's the moment, okay? That's the moment along this edge for region A. That's the direction of the moment, and the thumb gives the direction of the vector moment, right? And the same here for region A. What do you notice? Let's make a number of observations, which I want you to remember, because you don't want to keep doing this for every region, all right? Because you will be here forever. First of all, the vector moments, can you see? They are going in like a flow. They follow the same. So in this case, from right to left, right? So you have a flow here. You have a flow, like a flow here of the vectors going in the same sort of direction, from right to left in this case. So if I get this one, if I get only one of them, I can deduce the other vectors. That's number one. Number two, these moment vectors, as I said, are going like a flow from right to left. Can you see the moment rotation? The vector rotation? It's going in the same, it follows the same flow from right to left. Can you see that? Yes? Yeah. Then, once I've completed A, then what I'm going to do, for region B, these two here must be in equilibrium, opposite. So I can deduce this one. Yeah, equal and opposite. Again, these two here must be equal and opposite. Again, these two here must be equal and opposite. Okay, so now I've got all the moment vectors. Then, can you see the rotation vector, how it's going like a flow again, anti-clockwise? So once I've got one of them, I can deduce the others. So in future, if you've got a slab like this, or a triangle, or whatever regions you have, if you do one region, if you follow the equilibrium condition, and the fact that the vectors go in the same direction as a flow, then you can deduce for the other regions from that one region. Clear? Yeah? Okay? So you don't need to do it for all of them, you just do it for one region. Any questions on that? Okay? So there is a sort of pattern for each, for the slab. The reason we have done it this way is that now I've got the vector directions for the moments and for the rotations. And what I've done here, I've created the table, and this table, I have the four regions. I have region A, region B, region C, and region D. For each region, I'm going to obtain the moment of resistance in the X direction, the moment of resistance in the Y direction, the length of the yield line in the X direction, the length of the yield line in the Y direction, the rotation, okay, in the X direction, the rotation in the Y direction, and then the work, which will be M times L times theta. And you do it for the X direction plus the work in the Y direction. Let's do it for one region. I'm going to explain for one region. Look at region A here, this one. Okay, can you see the moment vectors? Please pay attention. This is the X direction, right? This is our chosen axis of reference. Do you agree that when you project these vectors and this one onto the X-axis, you get M? You agree? And do you agree it's minus because it's going opposite the X direction? You agree? So projecting these vectors here onto the X-axis will give me M. And it's with a minus. Right? Now I'm going to project the same vectors here onto the Y-axis. So when you project on the Y-axis, do you agree that these two vectors projected on the Y-axis will cancel each other? You agree? So I'm only left with this one. And this one, this vector projected on the Y-axis will give me 0. So the net is 0. Okay? Then this is the yield line for region A. Do you agree with me that this yield line here, when I project it on the X-axis, it will give me 4 meters? Do you agree? Yeah? Do you agree that this yield line here, when I project it onto the Y-axis, it gives me half of 3, 1.5? Agreed? Yeah? So that's done. This is the not tricky, but this is the part which is a little bit where you need a bit of concentration, okay? So, theta x, this is the vector rotation, okay? This is the vector of the rotation. you can see that the vector here is in the x direction and it's negative. So it's negative, okay? In the y direction, if I project it onto the y-axis, it gives me 0. Now, what is the value of this vector? What is the value of rotation in the x direction? In other words, this is region A, okay? This is region A. Region A, in this direction, we have 1.5. Okay? In this direction here, along the axis of rotation here, we have 4. So I have 4 in this direction, and I have 1.5 in this direction. Okay? What we do in the future, you can see what we did earlier, we had the delta, we had the delta here, isn't it? That delta does not appear anywhere in the equation. Why? Because it does cancel. The delta will just cancel because when you substitute it with theta as a value or as a function of theta, with the theta on the other side, they will just cancel. So it wouldn't make any difference whatsoever if I had chosen a unit displacement. Would you agree? If I say delta was 1, I would get exactly the same answer here. Are you with me? Yeah. So what we have done, what we do in there with the yield line analysis, we always assume that the displacement is a unit displacement. Okay. So you've got a unit displacement at this point here, by the maximum displacement. So if we have 1 there. Okay. So what is the rotation? What is the angle of rotation of this region? You need to think a little bit in 3D. So you've got 1.5, you've got 4, and so the slab is initially like this, okay? 1.5, 4, and then it rotates like this. So you have an angle of rotation. What is this angle here? What is the angle there? If this is 1, do you agree that 1.5, do you agree that that 1 is equal to 1.5 theta? Do you agree that 1 is equal to 1.5 theta? Okay, so 1 is equal to 1.5 theta here, you can see that. So therefore theta is 1 over 1.5. I've done a drawing here just to show you what's happening in this direction. You've got 1.5. Okay, remember the displacements are very, very small. So you've got, this is 1.5, this is 1, and this is theta. So you have theta is 1 over 1.5. Is that clear? Yes? Okay. And so this is theta x. This is the vector here. The rotation in the x direction is minus 1 over 1.5. And as we said earlier, because the vector is horizontal, there is no, when you project it on the y-axis, you get 0. Now for the work, we multiply the moment times length times theta in the x direction, plus moment times length times theta in the y direction. So we have minus m times 4 times 1 minus 1 over 1.5 plus 0 times 1.5 times 0. So that's 0. So you are left with m times 4 times 1 over 1.5, because minus by minus is a plus. So you have 4m over 1.5. Is that clear? And then you can do it for region C. Region C is identical to region A, except that you have got the vectors here in opposite directions. Okay, so you have a plus and a plus. Otherwise, the net work for region C, as you can see here, is identical to region A, which is not surprising because we have got symmetry, right? So region A and region C have got the same work. They have the same, they have different signs for the vectors, but because when you multiply the vectors together, you get a plus, so you get the same answer. How about region B? Let's look at region B. For region B, we have a triangular shape. Okay, the displacement here is 1. All right. First of all, let's look at the vectors. Can you see? Focus on region B, please. Do you agree with me that when I project these two vectors, this one here and this one, on the x-axis, do you agree they will cancel each other? You agree? Yeah. So 0. Now, when you project these two vectors here onto the y-axis, do you agree with me that you get a positive answer? And do you agree we have 0.4 as given? So these two here, projected on the vertical axis, on the y-axis, will give me 0.4. And it's positive going up. Clear? Because that's your moment of resistance, that's your maximum. Clear?
Go through what's the maximum.
Sorry?
Can you go through how you work out the 0.4?
The 0.4 is given.
Oh, okay. It's
given in the x direction is m, and in the y direction is 0, so it's 0.4 m, that's given. This is data given to you. Okay? Yeah? I mean, I could have obtained this from Eurocode, as I was explaining earlier. If I use EC2, given some, if I know the reinforcement and so on, just imagine that we've got this from the code. So you have m in this direction and 0.4 m in this direction. Okay, so we have m and 0 in the x direction. Now, again, look at this. Can you see this yield line here for region B? When you project this yield line on the x-axis, do you agree with me it's 1? Yes? Yeah. And this yield line again, when you project it on the y-axis, do you agree it's 3? Okay? So we're projecting this yield line here onto the x-axis, we get 1, and on the y-axis, you get 3. Okay? Now, this is the rotation vector. The rotation vector is in the y direction. So on the x-axis, it's 0. And on the y-axis, what have we got on the y-axis? If the displacement at this point is 1, and this region B rotates about this axis, what is the angle of rotation of region B? What is this length? 1. What is the displacement out of plane? 1. So you have 1 over 1. Is that clear? So you have 1 over 1. 1 in this direction, and 1, which is the unit displacement. So you have 1 over 1. So you multiply then mx by lx theta x plus my times ly theta y, which gives you 1.2 times m, not meters, times m. And it's identical to d. So your total internal work will be the sum of all regions A, B, C, which gives 7.73 times m. 7.73 times m is the total internal work for this slab. Okay? So we finished the internal work. Now we're going to look at the external work. And remember, the external work is the UDL times the area for that region times the average displacement. Okay, UDL times area for the region times the average displacement. So let's do it for each region A, B, C, and D. Are we okay to move to the next slide, please? Have you got any questions? Any questions at all? No? Okay. Okay. We know that A and C are identical, so I'm going to do it just for one region, A, which is identical to A. C and A are identical, okay, here, right? And then D and B are identical, so I do it for one region only, all right? And then I multiply by 2. For region A or C, okay, this is region C. We have 4 meters in this direction. We have 1.4 meters in this direction, and it's supported along this edge. Remember the displacement here. Please pay attention. The maximum displacement there is 1. Okay, so the displacement here is 1. Okay, now for the external work, I am going to divide this region into 2 triangles and a rectangle. Okay, the 2 triangles here are identical, and I have a rectangle in the middle. Now, for the rectangle, please attention. For the rectangle here, we have W, the UDL, times the area. The area is 2 times 1.5. Okay, then times the average displacement. The displacement is 1, so we take the average, so it's 1/2. Okay, plus for this triangle, it's W times the area. What is the area of this triangle? The area of this triangle is 1 times 1.5/2. So that's the area here. And then the centroid is here, it's there. This is the centroid of the triangle. And if this is 1 here, you've got 1/3 there, the displacement, isn't it? So we have 1/3, and then you multiply by 2 because we have 2 identical triangles. And then when you rearrange and simplify, you get 2 times W. It's very simple, okay? So you just divide your region into simple shapes and add them up together, it gives 2. Now remember that A and C are identical. A and C are identical, so I have 2W for A as well. Now, when we go to region B or D, this is the triangle. So now we are looking at this here. Okay, we are looking at this. So we have 3 meters, and we have 1, and it's simply supported on this edge. So we use exactly the same. We have W times what is the area of the triangle? 3 times 1/2. That's the area of the triangle, times the centroid is there. So if this is 1 here, so if you get 1 there, the maximum displacement is where, and because it's a third, the displacement will be a third, so the 3 and the 3 will cancel, and we have 0.5 W, and it's the same for B, 0.5 W. So the total external work will be twice 2 plus twice 0.5. So 2 times 2, 4, and then 2 times 0.5, 1. So the total is 5W. So the total external work for this slab is 5 times the UDL W. Clear? Any questions on this, please? Is it clear? Okay. So what you do then, we equate the external work to the internal work. So we say the external work is 5W. The internal work is 7.73 times M. So now this gives me a ratio of M over W, which is 5 over 7.73, which gives 0.65. Or you could have M is equal to 0.65 W, or W equals 1.55, which is 1 over 6.5 M. Depending on the nature of the questions that you get, whether you have been given the moment from the code, so you know M, and then you can determine the collapse load, or you have tested your slab in the lab, and you know the collapse load. In that case, you use this equation, and then you get your M straight away, because you know W, okay? Or you can give, if you don't know either, you can give the ratio M over W is 0.65. Is that clear? Yeah? So it all depends on the question that you get, or what is known or not. Okay? So, and this is what I've explained here in this paragraph, that if you know the moment from the code, from EC2, for example, then you can determine the collapse load and vice versa. Any questions? This is a very good example where we have used how we use the sign convention, okay, and work in 2D. So it's not really that difficult, and you can see why we needed to represent the moments and the vectors, and the rotations are vectors, because then I can work about the two axes x and y. It makes it easy this way. Okay. Are you okay? Any questions? No. So next week, I think we've done. Yeah, that's it. We finished. So next week we are going to look at more examples of slabs. Next week we have 4 hours. I may be able to finish next week, and then use the week after as some kind of revision. We'll see how it goes. Okay. Thank you.